Okay, so good afternoon, everyone. Welcome to the course. Welcome to the lecture today. Today we're gonna be looking at lecture 3. So let me share my screen. Please let me know if I'm not audible or if you cannot see the shared content on the chat. Okay, so I assume everybody can see the slides as well as can hear me. If not, do something on the chat so that I can figure out the issue. So I'm gonna start with some parts which I left out last week, mostly about the. I'll just recap CNN layer and then talk about the pooling layer. And today we'll look at some more interesting aspects of working with CNNs. The key items today will be about transfer learning, which basically implies how to use a pre-trained CNN where you have already figured out a good set of parameters, the W's and D's, for example, and then how to use those same parameters essentially for a slightly different task that you have. Maybe you built a CNN-based classifier to do 10 class classification, and then you can reuse those parameters in some sense to work with a slightly related, maybe 3 class classification problem. Okay. And so transfer learning will be the main item. We'll also look at, so before that, we'll look at how to understand how CNNs work from a few perspectives. It's a highly nonlinear function at the end of the day. So there are a few ways to try to understand whether your CNN, what it's doing is actually, what you intend it to do. And then the third part will be, we'll look at a couple of additional techniques. One is called dropout. The second one is called batch normalization. And the third, which is more related to data pre-processing, is called data augmentation, which makes sense for images quite naturally. Okay, so these are three techniques we'll look at towards the end of this lecture. So let me start with last week's description of CNN layer and then the pooling layer, and then we'll get to the three main topics today. Okay. But before that, in terms of some logistics, I strongly suggest that you form teams if you have not yet formed teams, and communicate that with the TA. Actually, there's one lecture, one lecture session that we've allocated towards the intermediate project deliverable. So I think it's after, so today's the third lecture, so after 3 more lectures. So it'll be good to, and of course you have to submit your assignment soon, first assignment. So you need to have the same group for that. So definitely make groups and start working towards it. Okay, so with that, let me start from here. So last time I was explaining what the convolution layer was, and I was thinking in terms of a block diagram, tensors, and tensors were the input and tensors were the output. And so there was this notion of a filter. Okay, so conv layer essentially is a collection of filters. Filters are, think of them as small cuboids, and each cuboid will produce a slice of the output tensor. So output tensor is 3-dimensional. Okay. And so a slice of a 3-dimensional tensor is going to be a matrix. So each filter will do some, we'll talk about the computation of each filter is going to interact with the input tensor and produce one slice of the output tensor. So basically we'll produce one matrix. Okay. And then you stack those matrices together and you'll get the output tensor. So if you have 10 filters, you'll get 10 matrices. And so your output tensor depth will be will be 10 units. And if you use 30 filters, then your output tensor depth will be 30. Okay. So the only thing that remains to understand is what does each filter do? So how does each filter produce a that matrix? Okay. So that we can look at from this diagram. Okay. So what's happening? So here X is actually a if you look at the left column here, so this is a input. Okay, so this input is actually a tensor. It has depth 3. Okay, so which means that it is collection of 3 matrices stacked on top of each other. And so the actual matrix you can see is in the light purple area. Okay, so that's the matrix, the first matrix. The second matrix is in the, this is the second matrix. And this is the third matrix. Third matrix is cut off a little bit. Okay, so that's the matrix. Okay, now last time I said whatever input tensor you have, you can first there are 2 additional attributes that you could choose while operating with a filter. One was what is your stride, as in how will you move, and the second thing was how, whether you'll add something called zero padding. Okay, zero padding just means you put in zeros around each of the matrix slices. So the input volume, so the input tensor, for example, the first matrix slice here has a zero padding of 1 all around it. Okay, so which just means that you can see the gray area is all zeros and it's only of cell size 1. So although the original input was 5 cross 5, I mean this matrix, the first matrix here, matrix slice was a 5 cross 5 matrix. Now it has become a 7 cross 7 matrix. Okay, so that's on the a little bit of pre-processing that you do on the input with zero padding. Now, so why do we need padding? I think there's a question about it, about this, which is why do we need padding? And in fact, we also had the similar question last time as well. So again, this is many of the things that you'll see today's lecture and through this course. There are a lot of design choices, and some of these are heuristics. There is, of course, a justification for why we need various things. So, for example, for padding, the idea is that the filter, if you don't do a zero padding, then the filter may not be able to detect things which are at the boundary of that tensor. Okay, so for example, if X itself was an input image and you're searching for a star, okay, it's a, maybe it's a image of the sky, and maybe the star is at the edge of the image and you'll not be able to detect it, for example. So it's just to increase the increase the area that the filter sees in some sense. So that maybe if the filter is actually detecting edges or colors or maybe the presence of a star, hypothetically speaking, then having zero padding will at least give some signal to it. Okay, why is it 0? Why not some other number? You can certainly put some other numbers there. Okay, so that's another design choice, but people don't do it. So people have converged onto zero padding as one way to deal with the edge effects, okay, edge issues. Yeah.
If we put anything other than 0, aren't we like changing the input then in some way?
Yeah. So anything that we do, anything we're adding to the input is definitely changing the input. So not just zeros. So zeros have the nice property that they will not change the. So they're just, for example, if you look at the top left here, those zeros multiply with corresponding numbers in the filter matrix, but those multiplication leads to value 0. So they don't really affect, in some sense, the computation. But any additional number that you put, whether it's 0 or not, will certainly change something. Okay, so you can, for example, since the images are between, let's say in this case, in this example, the numbers in the matrix, original matrix, are going between 0 to 2. Okay, so you can always put the median value or the mean value, let's say 1 all around. Okay, so that is still fine, but it's a question of whether that serves your purpose. So there was some intuition for zero padding, which is to get some some features like edges and so on, which are at the boundary region of the input. But you can always put something else if that works out. Okay. At the end of the day, we care about the exploitation of spatial invariance with the conv layer. Remember, there were some aspects. So essentially, the conv layer is taking care of taking into account that whether the feature, the image feature is at the top left or the bottom right, it really doesn't matter. So the filter should use the same weights to work with all the regions of the image. Okay, so there was that spatial invariance aspect that it was taking into account. The second thing is, as a benefit, you're getting parameter reduction, because if you only have 10 filters, there are only 10 sets of parameters, and so the neuron output, think of the slice, each output slice on the output side. Each slice, even though there may be so many neurons, each slice corresponds to a bunch of neurons. All those neurons have the same weights. Okay, the weights essentially are the filter weights. Okay, so there's a lot of parameter sharing going on. So that's what we briefly discussed last time. Okay, but let me recap the filter operation anyway here with this example for others. On those who know, just it's a recap. So here, let's assume we have two filters, so W0 and W1. And because the input depth is 3, each filter's depth has to be 3. So that's why there's 3 matrices, and therefore the filter is a cuboid with depth of 3. And we just chose 2 filters. Because we chose 2 filters, the output depth has to be 2, and that you can see that there are only 2 matrices in the output. Okay. Now, so let's focus on the filter W0. Let's focus on the filter W1. Okay. So we can pick any filter. So let's pick filter W1. So filter W1 to produce one number on the output. So the one in the green box here, it will multiply element-wise each matrix that it has. It has 3 matrices to each of the matrices on the input. So you can see the relation. So this first matrix multiplies with the first matrix. So the second matrix multiplies with the second matrix, and the third matrix multiplies with the third matrix, element-wise. Okay, so it's not really matrix multiplication. So and then also because the filter height and width are 3 cross 3. First you go to the top left. Okay, because we added 0 padding, the top left is these bunch of numbers here. Okay, you work with the top left for all the 3 matrices. You get some intermediate numbers, and then you add them up. Okay, so the added number is this one here. Okay, and we also have a bias with the filter. It's just one other offset type of a thing that you can add. Okay, and the number is, these numbers are all tunable, by the way. So everything inside the filter, these ones and minus ones and zeros. For this illustration, these numbers are just fixed here, but these are the numbers that we're varying when we do gradient descent. Okay, these are the parameters actually. These ones in the red. Okay, area. So filter W1, when it acted on the top right, top left, it produces number 1. Okay, and then because we chose stride, I think we chose, we chose stride 2, I think here. The stride is 2 here, so that's why we get a. So the next computation is happening on this block. So okay, this block. So we went 2 steps to the right. Okay, so and then again, if you go 2 steps to the right, you get the third box. Okay, so that's how you move the filter on this input slice, and each of the slices is the same thing. So the stride here is 2. But that's again a choice. I mean, you don't have to pick 2. You could have chosen a stride of 1, then you would have gotten a different size output. Okay. In fact, the different size output would be 1. The output size would be 5 if the stride was 1, right? So here's a very simple heuristic or rule of thumb. If you do 1 0 padding, and if you're doing a stride of 1, the output size is going to be the same as input size. Okay, as for square for square input tensors. Okay, it doesn't have to be for square, but I'm just saying that that's the rule of the thumb. You can get the precise output dimensions based on your choice of 0 padding size and the stride. But is this computation clear? Any questions about what's happening in terms of output? So this first number is because of the looking at the top left corner. The second number 3 is because of the top center area, and the third number is because of the top right area. Okay, which is 3 cross 3, and that's because that's just for filter 2. This is for filter 2, and this one is for filter 1. Okay, first matrix, and then and that's a tensor because it has a depth of 2 because we have 2 filters here. There's an animation at this link, but I will skip that. So any more questions about the con layer? So this is the operation. So we are going into the gory details of the operation just to understand what is getting multiplied with what. But in terms of intuition that you want to take away is that these filters, each one in terms of interpretation, each filter is trying to detect something, something which is the same pattern across the image. And that's why it's looking through each subregion in the image to find that pattern essentially. If we are talking about filters right at the right before the input layer, which input layer is essentially the image. But if you think of a con layer, which is like the third layer, the fourth layer, it's kind of hard to really interpret uh, what exactly is going on. But the intuition is the same, that there is some spatial invariance that is being captured with the filters, and there are less a number of parameters as well. Okay. So that's the con layer. So at the end of the con layer, you get a tensor, right? In this example, the tensor was a 3x3x2 size tensor. So there's a question, given that the weights in the filter get updated, how do you control the extraction factor? So, and want the complete face to be extracted in terms of feature. So, okay, so there's a question about filter weights getting updated. So here's the thing, right? So what's the history behind using a con layer is that a lot of previous work in image processing, and you can still use those ideas today, was to design hand-engineered filters, which would detect edges, color gradients, and so on. Okay, so so those had fixed numbers. You would not change them. So they would be like fixed feature extraction. So if you use that filter on an image, you would detect a bunch of edges in certain regions, and for example, and then the presence of those edges, for example, would indicate that there's a face of a person versus a face of a cat, for example. Okay. Now, in the neural network parlance, it's all these numbers, these filters don't have to be interpretable. Okay, all they have to do is change those numbers, in which essentially are the filter weights, to maximize our discrimination between the classes. If we are doing a 10 class classification, the filter weights themselves are, whether they detect particular explicit regions, like edges themselves, is not very, is kind of post-hoc interpretation that we're giving. If the con layer happens to be very close to the beginning of this neural network, which is like if it is right in front of the input layer. Okay. By the end of the day, the weights are completely data driven and they'll get changed using backprop. Now the question is then, if they're only looking at a small region, if these filters, then how are they, how is the whole network essentially detecting let's say the whole face? Maybe, if that's the direction of the question, then you can see that the filters, I don't know if I have the picture here. Yeah. So you can see that maybe these pictures are fine. So you can see that, like for example, this neuronal output here, it's only depends on this part of the tensor, input tensor, right? So you can say if it's at the beginning, let's say this was the image itself, and this was the first con layer output, then this filter is actually only seeing a small part. So it's not really seeing the whole face, right? Maybe like the nose or something like that. Now, but if you think about it, if there's a con layer later on, okay, if there's a con layer later on, whose output is a tensor, that neuron is going to look at a small part of its input, right? Very similar to this diagram. But each neuron there looks at a small part of its input, and each neuron there, if there are many con layers, will look at a small part of other input. So this neuron is actually looking potentially at the whole image. Okay, if it happens that the con layer is later on in this layered architecture. So, as you go up, so from input layer, the immediate next layer may not be looking at much of the images, the intermediate computations, the intermediate neurons, neuronal outputs. But if you go closer and closer to the output layer, so those neurons tend to look at the whole image. And you'll actually today, maybe we'll come back to this, we'll see some figures at different layers to understand what those neurons are seeing. Okay, but so let's wait Suhas for that again, okay, in a few minutes.
Is there like any trick that like just looking at the numbers in the filter, that you can see this filter will maybe detect vertical edge or
Yeah, yeah. I think there was a link. I believe I don't see it here. Uh, there's a link which shows how the hand engineered filters, how do they detect. Uh, Sorry, I'm looking at the sources links here to figure out if I have the link. Oh yeah. So go to this link. Maybe I can just show it to you right now. Which shows how this works. So let me open it. And you guys can open it as well. Okay, so sharing. Yeah, can you see my browser screen? Okay,
Yeah.
so here you can see a little bit of intuition, especially if the con layer is at the beginning. So this is an example of a 3x3 filter. So 1 0, so 1, sorry, 0 minus 1 0 minus 1 5 minus 1 and 0 minus 1 0. So sorry, yeah.
And higher the number is, the more darker the color, right? In that filter.
Uh, Higher the number in the filter, the dark. So no, so okay. Let me just. So your question is about. So there's a bunch of filters here, hand engineered filters. Okay.
Okay.
So different numbers correspond to different things, but it's actually, is it working? I'm trying to see. Oh yeah, yeah. This sorry, that picture. I want to show this picture. So this is how the filter is operating, right? So this is the input image on the left side. You can see the 3x3 filter here, for example, the red area.
Yeah.
I can't point there, but you can see the red area on the left figure, right?
Yep.
So, and then the pixels there, this is a grayscale image, so it doesn't have a depth, okay? Depth is 1 for this image. And the grayscale image has these numbers there, okay? 178, 179, 182, those are the pixel, the intensity values. Okay?
Mm.
So this grayscale image, since it's scaled between 1 to 255, okay? So if you go to the white area, you can see that the white area is 255 essentially. If you go to the dark areas, it's basically very close to 0. I mean, I don't think there's a black here, but essentially very close to 40s, let's say here in this example. But if you look at the operation of the filter, it's essentially multiplying element wise. Since the input depth is 1, your filter depth is also 1. So a filter is just a matrix here. It's 3x3, and you can see what the filter did in terms of the output. So it's just sharpening the image. But you can also do you can also do other things like blur the image and so on. So for example, this filter is finding edges essentially, because it's looking at some sort of a change from the top color to the bottom color, and if there's a huge change from, let's say, the black area to the white area, it's drawing an edge. Drawing this. I mean, drawing the white line, or essentially that number is high. Okay.
Okay.
So this is how filters work, hand engineered filters, and this is the idea or the history behind the notion of filters in the con layer. Does that help answer your question?
Yeah, sure. Yep. Thank
I
you.
mean, so this is so with CNNs, we are going to give some post hoc justification in terms of what the filters are detecting. Okay. But they have roots in this type of engineering, feature engineering that was done before. Let me go back to the slides. Yeah. Okay. Yeah, but the key takeaway here is that we at least understand what's the low-level computations happening. But at the high level, it's basically aggregation of spatially invariant aspects of the input tensor. Okay. If there's some high numbers in some region, for example, for the input region, maybe they correspond to something. Okay, so that's what we are detecting. Okay, that's what the output hopefully represents and retains. So as I was saying, in this example, the output is just a 3x3x2. Sorry. Wow, what happened? Uh, oops. Okay, is this the same? Oh, I went to the next lecture. That was not correct. Okay, so the next layer is quite, now it's using my hand. Okay. So the next layer I'm going to talk about is the pool layer, which is quite intuitive. It's basically just trying to reduce the size of the width and the height of the input, its input tensor. So if you do a pool, it's like a function, right? It takes a tensor as its input, some box, cuboid thing. All it's going to do is, let's say if this is the depth, okay, depth, then it doesn't affect the depth, okay? So if you do this operation, you get something which is the same depth, but try to influence the height and width. Okay, so this size and this size. Okay, that's what we're going to do. And what is the need for doing this? We want to reduce the number of numbers in this tensor. Okay, so if the tensor had 100 cross 100 cross, let's say the depth is 10, this depth, let's say because there were 10 filters before. So we're just trying to reduce this 100 cross 100 numbers per slice. Okay, and how do you do that? You just, as I said earlier, you retain the input depth. So this is the input tensor. The pool operation, the pool layer or the pool operation is going to produce another tensor, which is this. Okay, the depth, which is 64, remains the same. But it's just that the height and width have been changed to, in this example, changed to half of the what they were before. Okay, so if you really want to think in terms of if you because you can always represent the matrix as an image. So if you look at the intensity of this matrix, like if you plot it with IM show or something, then you can see that the output matrix may retain some of the features, but with lesser number of numbers, because clearly you lost, like this used to be this size, you got rid of this, and this. Okay. Now, how do you do that compression? Is is quite intuitive. For example, if this was the input tensor, input tensor slice, okay, a single slice, a single matrix, then you just operate slice by slice anyway. And if you have what is called a max pool operation, a certain type of pooling, then you look at, and if it'll also, the pooling operation will also have a size. Okay, 2 cross 2 will generally reduce the width and the height of the input by half. Okay, 3 cross 3 by 3, and so on. Okay, so if it's the 2 cross 2, a max pool operation is essentially taking the maximum of these 4 numbers and keeping that in the output. Okay, so that's the operation happening. So you can think of a function call, right? So define a function, right, which takes the input tensor and just says, okay, for the first for the first 4 numbers, retain the max of those 4 numbers, and so on in a for loop, right? You can write that function. So that's what's happening here, and the objective is to reduce the number of numbers. There was a question from an earlier part, which is, you mentioned the grayscale image has depth 1. So as it always good practice, reduce the input size by converting images to grayscale. If you think color information is not useful for classification, right? So maybe there are some, certain supervised learning problems where color information is redundant, then you certainly can remove the color. But sometimes color does give a sense of, to disambiguate 2 different classes, you may need color. Okay. So I wouldn't say a priori it's a good heuristic to start with, but you can certainly try it. Like, for example, the MNest images are all grayscale for those who worked with it in, for example, 575. Okay, let me come back to polling. So it's one, I guess, layer to help with managing the number of numbers, because if you recall in my previous connection, at least in the previous lecture, I was talking about input image and then a con layer, and then I think a pool, and then a fully connected layer. So the fully connected layer is essentially doesn't really care about the doesn't really care about the input tensor shape as such. Whatever is the number of numbers. Let's say it's a tensor is again guess 112 cross 112 cross 64, right? That was the example 2 slides ago. Then this fully connected layer, every will produce some output tensor, but that output tensor, each number corresponds to a neuron, right? That neuron essentially has to be connected to every coordinate here. Okay, so polling is really to reduce the input tensor size for the fully connected layer. That's kind of its use. So that's polling. Fully connected layer, as I was just saying, we have already discussed this before, is essentially the layers that we saw in feed-forward neural networks. Okay, so there is an example of an example of a CNN architecture. A CNN architecture is essentially any layered sequential neural network where there are a bunch of convolution layers, which are the prominent layers in that net architecture. Okay. The CNN will also have, for example, some fully connected layers, can have some fully connected layers towards the end of its, closer to the output layer. Okay. So you can refer to this link to look at an example architecture. But I think in today's lecture, maybe towards the end, we anyway have a CNN example in our one of our notebooks. So I can try to spin that up, and we can go over the code because it's also written in PyTorch, so it'll be helpful to go over. Okay, so that's CNN. Any questions at this point? Before we'll actually keep revisiting ideas about CNN today. Okay, if there are no specific questions, and certainly ask questions as we come across a few. In fact, the first part will be trying to understand a little bit more about CNN. So if there are any questions, please ask at that point as well. So today, as I said at the beginning of this class, there are going to be 3 parts. First part will be trying to debug essentially and understand what given CNN model is saying. So let's say you've already trained a convolutional neural network using gradient descent techniques, one of the techniques in that first order family. Then you want to now understand what is your CNN doing. Okay, so for example, for a linear model, you would just look at the coefficients and get a sense of maybe some feature coordinate is important or not, or maybe if you had even a nonlinear model, you could probably do and if the features were interpretable, like in a not image setting but a more tabular setting, then you would do compute feature importances. Okay, and you've done that, for example, with random forest and so on. So there's some way to understand what your trained model is doing, right? We'll kind of look at similar analogous techniques now. And then the second part will be transfer learning, and the third part will be these 3 things: data augmentation, bash norm, and dropout, and a little bit about weight initialization and how it's relevant to the optimization part. Okay, so let me start with visualization. Let me skip this recap. So you can kind of refer to this slide to just get a sense of why there is a reduction in parameter count, and really intuit why having fully connected layers, too many fully connected layers all the way from input to output will really blow up the number of the number of parameters you need to update or train. Okay, so we'll not get into the detail of backprop through a CNN because, as you saw, the filter operation, there's a weight sharing across multiple output neurons. So if you recall from the backprop lecture, lecture 1, if the gradient, if a computation, so if the same parameters are being used and then the computation is going to different outputs, then you'll have to sum up gradients. Okay, so there's some summing up of gradients happening while doing backprop through CNN, because it's the same parameters, they're influencing multiple outputs. Because multiple neurons on the same output slice, they all use the same weights to compute, right? So you need to do some aggregation of gradients, but we'll not go into the details of backprop here. And similarly, backdrop through a pool operation is also, you need to just intuit how it works. Just like, remember, ReLU had this gate type of intuition that if the input number was positive, when there's a gradient backdrop operation going on, you just, whatever gradient you got at the output, you just pass it back to the input. But if your current number was a negative number, then you wouldn't pass the gradient. Similarly, same thing happens with pool operation, okay? Because, for example, the pool operation would be max of 4 numbers, A, B, C, and D. If the number A is the maximum, then you kind of have clipped out, B, C, and D are not influencing the output. So passing back gradients to these 4, you just have to look at, basically you will not be passing gradients back to B, C, and D. Okay, the gradients should be 0. I think you can double check this offline. Okay, but let's get to visualization, which is once we have a trained model, which is that once we have a trained weights, right? So filter weights. I don't think so. Previously, we were using W1, P1, for example, and let's say W2. B2 to represent weights of a 2-layer feed-forward neural network. I did not use explicit weight notation or anything for CNNs, but you can also imagine a similar representation. Okay, so it's just that W would be a tensor. If you W's would be tensors, and so, for example, W1 and W2 could be 2 filters at the same CNN layer. Same con layer. For example, you can just use that notation. So let's. So what we're going to do now is try to understand, once we have a trained network with a bunch of weights already set, maybe using backdrop with gradient descent, or there are many techniques there. What do we like? How do we know that the neural network is capturing the right features to classify, in your classification task? Okay, so for example, once the network is trained, it's a function, right? It's a function given input is producing some output. For example, the output is that, remember that P cross 1 dimensional output, where P maybe is the number of classes. Okay, so you already have this function with the parameters of the function, which in our case are the weights of the filters and the biases. How do we interpret this function, right? So because it's a layered architecture, you can always compute intermediate output. So at the output of each layer, there's a tensor. Okay, you can just try to interpret intermediate outputs, right? Intermediate tensors for this input that you have. So when you have X, that network is already trained, you can produce some tensor at some layer and try to understand it. But it's really hard to understand those tensors. So we'll look at a few attempts in this direction. One is to look at activations that are happening as you pass inputs through your trained neural network. We look at the weights themselves, as in the thetas themselves, the parameters. We'll also look at images in an embedded space, in an embedding space. So I'm going to talk about what is embedding as well, to understand whether your CNN is really able to discriminate between classes. Okay, and crucial to it is the neural network is going to produce this embedded space, right? So that's one way. And finally, you can also use occlusion as a technique, especially for image data. So if in an image you're detecting a dog, if you occlude the dog, you should not detect a dog, right? So is occlusion influencing your predictions? You can do that. And finally, you can also try to figure out which neurons get triggered at what images, what type of images. So, and this will partially answer, I guess, a question earlier, whether, if each filter is only looking at a local region, how are we, understanding that there's a face involved, and therefore maybe this image is of a person. So we'll look at some images which will help us get a sense of that. Okay. So this is actually just a CNN visualization tool. just gives you an idea of that local connectivity again. It's an in-browser animation, so I would highly suggest you guys look at it, but I will skip that. So let's look at the first technique. So just look at activations. So activations, remember, are just the output tensors. Okay, output tensors after they go. So each output. So remember, output tensors at the output of any layer are going to be the outputs of those neurons. Okay, so each neuron produces one number, and outputs of neurons essentially have already passed through the nonlinearity. For example, a ReLU or a sigmoid nonlinearity, or any of the other choices that we have seen. So we can actually try to visualize these output tensors. So for example, we can look at the in this case, we are looking at, so we have one square here is the output for each one filter. Okay, so remember, one filter produces one slice or matrix. So you can actually, and in this case, there are many filters. Yes, 36 filters here. So you can actually just plot these 36 filters using IMShow and get a sense of, and you can get a sense of, for a given input image, let's say a specific test image or some image that you have, a reference image, which of the neurons which of the filters are getting, are producing something. Okay, if the filters are not producing anything, then it means that the filters are, are essentially like producing a number, for example, less than 0. If you if the if we're using nonlinear, if we're using the nonlinearity being a ReLU nonlinearity. Okay, you can do that with in this example, the left figure shows about 36 filters because it's at the beginning, and the right figure shows there's a fifth convolution layer, so a lot of con layers, and in the fifth layer there's a lot of filter depth, so a lot of filters are there, and you can see, you can try to visualize which filters are getting triggered and which filters are not. Okay. So this will also tell you that, okay, you had, let's say, 100 training images, and it passed all those training images through your, let's say, the fifth con layer, and you saw that maybe there's a bunch of filters which are not at all, which are always 0. Okay, then you know that those filters are really not affecting anything, because for any input image, the output is always 0, so it's not really affecting any further computation. Okay, so that's one way to try to understand whether your network is there's the right parameters. Let's look at the second, but it's only a partial idea, right? It just gives a sense of whether your training was good enough that your filters are triggering and generating some output. Okay, non-zero output, for example. The second is to look at the weights themselves, try to visualize the weights themselves. This is not really related to inputs, but just the filter weights themselves. Okay, so the filters themselves, for example, let's say they're 3x3 or whatever, 11x11x3, for example, at the first con layer. Then you can, they look like images, right? Because the depth is 3, then you can actually just think of them as images, and we can plot them. And it gets harder if to plot them as images if you move further along into the if you move further along, as in you look at layers which are more deeper. Is there? Okay, that was a question from before. So you can visualize weights. So for example, I think the most useful thing about visualizing weights is at the first layer, the weights do represent as if they're detecting edges. For example, you can imagine this filter may be detecting essentially will detect an edge because of the numbers being such that numbers in this direction are high, and numbers right before and after it is low, for example, in that region. So maybe it detects an edge. Okay, so you can interpret that, but the moment you go to higher layers, it's kind of hard. And the depth will also depend on the input depth, and if the input depth is not 3, then it's hard to visualize them. Okay, but I think the more interesting techniques are the next 3. So let's look at visualizing the embeddings. So embeddings are just the function computation. So let's take an image X. Okay, it passes through the CNN and it produces scores, right? for example, scores, which are p cross 1. And then you do a softmax transformation, and then you get a probability that the image belongs to class 1, class 2, or class 10. But you can actually take the intermediate computation. So, for example, let's say the function is let's say the function is, so finally when you're getting the scores, let's say to get the scores you will do a linear transformation, right? A linear transformation of its input, which is let's say its input is actually there's a nonlinearity before, so there's a max of 0 comma h. Okay, so this is called the activation at the penultimate layer, and h is the pre-activation. Oops. Okay, so you can look at this whole thing in blue as the activation, and you can think of that vector. Okay, so before we got the scores, we can get the input to the score computation, which is this is just a linear transformation wx, so w times its input plus b. So these a's is what I'm talking. It's a vector, or it can also be it's going to be a vector because we are looking at the penultimate. When we produce the scores just before we got the scores. Okay, the scores we got were some linear transformation of some inputs. We just want to look at those inputs. But those activations may be informative of whether your CNN is actually doing good discrimination between the classes. Okay, so this activation vector, so you can produce one vector for each training example. So they can be thought of as a representation of the input image, not just those guys, those activations, but you can go 3 layers down, and you can consider any intermediate tensor as because all these are activations, these are outputs of neurons. You can consider any of them as representations for your input image. Okay, so whatever is the image here of a person, let's say, any layer activation, you can think of that as a representation. And this representations, the people use the word embeddings to also call these representations, okay? or just vectors. Now what you can do is, let's say you took the representation of almost, except for, the input that went into the score computation, you can project those vectors back into 2 dimensions, because it's very hard to visualize vectors beyond 3 dimensions. So project this vector here, A, into a 2-dimensional or 3-dimensional space, and hopefully the projection operation is such that it preserves distances, in the sense that if 2 vectors were kind of similar to each other, and so there may be the distance between them in appropriate notion of a distance metric is small, then in the 2-dimensional projection, the distance remains small. And if the 2 vectors were very far away in the appropriate metric, then in the 2 dimensions, they are still far away. If the projection had that property, then you can visualize whether your CNN is doing a good job in segregating or basically discriminating across classes, between classes. And so you can see there are many ways to do the projection. So there are some names that I'll throw out, TSNE, and there's a more, I guess, recent one called UMAP. So just to give ground the idea, so AlexNet was the neural network that was used in the ImageNet competition from 2012. So that network's final layer, right before you compute the scores. Remember, in ImageNet is a 1,000 class classification problem. So you'll go from here to 1,000 dimensional score vector, okay, with that transformation w times this vector plus b. Okay, so you can look at these vectors, 4,096 dimensional vectors, as representations or embeddings of your images, of your training data, or you can get these embeddings even for your validation data. And then you can use, in this example, there's a projection operator, nonlinear projection operator called TSNE. So many of you have already seen a linear projection operator, which is, for example, you can do a PCA, right? You can PCA to reduce the dimensionality and project your data into 1 or 2 or 3 dimensions which capture the highest variance. So here we are projecting this 4,000 dimensional vectors into 2 dimensions, and then we can just because they're in 2 dimensions, at each point we are just replacing that point which corresponds to an image with a small figure of the image itself. Oops. It's a small figure of the image itself. And I don't know if you can see. So this is basically trying to show that, for example, square type objects are around the same area. And greenery is the same area in the 2 dimensions, and so on. So this is just a partial, I guess, validation that your network is able to discriminate modulo that the projection operator is good. Okay, it preserves distances properly. Okay, so that's that technique. I think this is always a good thing to do once you've trained, especially with image or images, because it's kind of easy to interpret and visualize whether your predictor is working well. Okay. Next is debugging by occlusion, which is that we want to. So let's say again we have a trained network. Now we want to figure out which part of the image is leading to a certain classification. Which part? Okay. Because sometimes, for example, if you want to classify dogs versus cats, and it just turns out that dogs the photographs for dogs were taken on green grass, whereas cats were taken indoors, then the green signal in the images may influence your classification more than the features of a dog versus a cat. So it's good to do that, and you can occlude and try to figure out how does the probability of class of interest change when you occlude things. And let's go over an example. For example, here is the figure of a dog. And so let's focus on the left column. So here, this image here is representing, so each square here is representing if you occluded, so this gray thing is the occlusion, okay, some median value for each channel, okay, some number so that it looks occluded. You can choose anything. You can have a black occlusion as well. So for that occlusion, there will be one number generated. Okay, so as you keep sliding the occlusion up and down, there'll be numbers generated. Okay, if you slide up, for example. So you can see that the moment occlusion comes here, I don't know if you can. I don't know if this is a good. No, not right. Okay, so where I've drawn blue, okay, where the occlusion is, that's where the color here is blue. So blue, so here I should have mentioned the intensity. Blue means the probability of that class is low. Class is 0, and then red means probability of that class is 1. Okay, so in this occlusion-based debugging, we occluded the face of the object in the figure, and that because we occluded it, it's saying that the probability of this being a class of interest, in this case dog, is basically 0. Blue represents 0. Okay. Similarly, you can try it with. So this is just, I mean, this is not scalable, but you can try this with a few example representative images. For example, here, the moment we are occluding the wheel, then it's not, it's not able to say that it's a car wheel. Okay, so everywhere else, if you occlude, it's still saying that it's a car wheel. Okay. Same thing with if you occlude the dog itself, then the true label probability of it being, if this image being of that of an Afghan hound, is going to 0. Okay. So that's debugging the occlusion. And the last one is about synthesizing images, which is more about trying to understand, especially neurons at almost the penultimate layer, or almost neurons which are towards closer to the output. So you want to figure out which type of images trigger this neuron the most. Okay. For example, and the way you do it is you already have the network f theta, and x is the input image. So you want to figure out. So you have this network. So let's say the network is producing a bunch of scores, right? So which means that, let's say, think of a score, then it's connected to a bunch of neurons in the previous layer. So let's pick some neuron here. Okay, so this intermediate neuron here, which is feeding to the output score, let's say if this neurons, let's call the number being produced here as z, then z is equal to some g of x as well, right? So the intermediate number that was produced here by this neuron's output is just a function of x as well. Now you can find, and it also depends on a bunch of parameters, all the weights which lead to that z. Okay. Now you can say you can try to find max over x of g of theta of x. Okay. So find any input or any appropriate image which triggers this neuron. Remember, this neuron's output is z. Okay, to maximize the output of the neuron, what the input should be. Okay, so with that, and you should not maximize over arbitrary x's, because image spaces you can keep changing every pixel by arbitrary values, and you get so many choices. So with you kind of restrict this max operation over a suitable range of these image values. Then, for example, if you pick a certain neuron, then you can see that so you're maximizing. So that's why something called, you do gradient ascent instead of descent. And you can see that for some neuron, maybe you'll get an image like this, and for some other neuron, you get an image like this. And it actually has some patterns related to how gorillas look like. Okay, some features that you detect. This seems to be quite low resolution. So there is a link here. You should try that. You should try that to get a sense of this idea. Okay. I mean, this is actually a better picture. So here you can see that you picked. So for example, in this case, I think they were looking at I think at the ImageNet dataset based classifiers. So there's a class goose. So you're trying to figure out what type of images would trigger the goose, the final, neuron corresponding to goose the highest. Okay, so you can see that this is the type of image which will produce, which will trigger this neuron to have the highest value. Okay, and similarly for ostrich, you will have. So this is the optimal image. If it was the input, then the ostrich coordinate would be highest value. Okay, so that's the idea here, to synthesize images. And you don't have to do it all the way at the output. You can do it at different layers. In this case I think they were working with VGG. I don't recollect, but you can do it at any layers. And if you look at what's the image that triggers certain neurons at the fifth layer, you'll see some level of features. They'll look at, as you go deeper and deeper, the features become more elaborate. Okay, so that comes back to that question about how are you detecting a face. The almost the final layer neurons, they will be able to see the full input image. Okay, and the neurons at the beginning, they only see small patterns. So layer 2, layer 3 are only looking at some small patterns that you can see here. Okay. But you don't have to synthetically generate an image that was not there in your training data set. You can also do something else, which is find an image in your training data set which triggers, let's say you pick a neuron. By the way, there are so many neurons in the network that you'll generally pick the neurons closest to the output and pick one neuron. Let's say for example, the score vector is going to be, let's say, 10-dimensional for 10-class classification. Then you pick one of the coordinates and figure out which images in my training data set are triggering this neuron the highest. Okay, it's again the same problem. Where is this? Again, it's the same problem. It's just asking which images X in my training data set are the ones which are ensuring that this coordinate is always is reporting the highest values. Okay, and so you can see that yeah. So basically, which images activate a neuron, and these are some examples of uh, images that are activating a specific neuron. So that's available at this link, but uh, you can trigger and see this. But this is, of course, manual, and it has a lot of choices to be made, like which neuron should I try to say that this neuron is important, and what images are triggering this neuron, and so on. So there's a little bit of choices to be made, and so you can read more about it in this link. Okay. Any questions up to this point? So these are all techniques to just understand. These are techniques a little bit specific to CNNs, in addition to all the other ways of diagnosing a trained model. Right, you can look at the histogram of activations or how the activations perform. You can look at the weight values themselves, distributions of the weight values, or you can do occlusion, or you can do projection of the embeddings, or you can do the final thing, which is figure out the example representative images which trigger um, output scores to be highest for each coordinate, for example, and hopefully the outputs, the images which trigger, let's say, the first coordinate score to be the highest are very different from the images which trigger the second coordinates score to be high enough and to be high. Okay. So if there are no questions, then let's take a break now. And then when we'll return, we'll look at transfer learning and the tricks that I mentioned. Okay. So we'll come back at 4:45. Nope, we are recording now. Okay, so we missed a part of the recording. Let me quickly recap what we did for those who watched the recording. So I started with transfer learning as an idea where you use a network trained on one data set as a way to learn another classifier, okay, on a different data set. So you want to work with.
अभी तो ऐसे बैठा हूँ भाई.
Somebody did not mute themselves. Okay. So transfer learning was about using a network trained on one data set to for another data set. And typically the first data set would be really large, like ImageNet, and somebody else has already done the hard work of building that network. And the second data set would be some other data set which hopefully has some similarities with the first data set. And so you can essentially do what is called transfer learning. And in this case, you don't really need a large amount of data for doing this, to learn a classifier for your specialized data set. Okay, and there were two techniques: feature extraction based approach and a fine tuning based approach. Feature extraction is all about using the pre-trained network and just generating these embeddings. So remember, when we did the debugging of CNNs using embeddings or representations of the penultimate layer, you can just use the penultimate layer's output. If it's a tensor, reshape it so that it's a vector, and then you can just think of that as a vector x prime, which was generated from a vector x. And so for every input example x, you can generate a vector x prime. And so this x prime is called the extracted feature. And then you just use x prime comma y, which are the labels, in another simpler model like a logistic regression model or an SVM model. Okay, and so essentially what you've done is extract features from x to x prime. And this still works where x and x prime are not related to the ImageNet data. So maybe x and x prime, sorry, maybe x's are related to your task. For example, maybe you're classifying dogs versus cats. Okay, so these class labels are different from the ImageNet class labels, but you're still able to do this because the data sets have some similarities. Okay, and this was an example of how to do that with AlexNet. AlexNet has the penultimate layer has a 4096 dimensional vector, so you can generate these as you can use these vectors as your new features. Okay. And I was briefly commenting on the fact that if the data sets are very similar, then you can extract features from closer to the output. And if the data sets are quite different, then maybe the layers which are specialized to the first data set are irrelevant for your data set or your task. And so you can probably use the embeddings from a more layer which is closer to the input. Okay. Now for fine tuning, the idea is very similar, but you don't just feature extract and forget about the original pre-trained network, but we use the original network and just append, or not append, but modify the final layer, a final layer or the final few layers into the layers that you choose. For example, let's say the original network had two fully connected layers at the output. You can change both of them. You can change one of them, such that, of course, you need to match the number of classes that you have in your problem. For example, you may only have a 2-class problem. And then what you do is change the, you're willing to, I mean, you could learn you will have to learn the weights here anyway, but you're also willing to learn the weights of a few layers down, okay? Maybe even all the way down if the data sets are very dissimilar. But if the data sets are similar, you may be willing to slightly modify the weights of the previous layers. And the way you do it is to set low learning rates in the learning rates are just parameters of the optimization routines. They are present in multiple variations, like, and we'll talk about optimization in a later lecture. So something like stochastic gradient descent or ADAM optimizer and so on, they all have learning rates. So you can change the learning rate. So you keep the learning rate very low. That means that the weights are not changing much. Okay, so you can keep low learning rates for the layers which have been which exist from the previous pre-trained network. Okay, and so that's called fine tuning. You're just slightly changing the parameters around their values from before. And here we were just seeing an example of the benefits. So a straightforward, use of a pre-trained network was already giving a good performance on, for example, object classification task. But image-specific tasks is not restricted to just object classification. There are many tasks, and maybe later on in this course we'll look at object detection. But there are many types of tasks: classification, detection, retrieval, and so on. And for many of these tasks, you can use these pre-trained networks as feature extractors, and get a boost. Okay, so that was what we covered before. So, and as I mentioned, there are different tasks. So, for example, it's just to give a sense of a couple of other concrete tasks. So, classification is just trying to detect a label, give a label to an image, and the classification plus localization means you need to produce a label, so maybe 1 out of 10 labels, but you also need to produce 4 numbers. Okay, the 4 numbers are essentially the bounding box or some sort of a box around the object of your interest. So you're not just saying, oh, there's a cat in this picture, but the cat is between these 4 coordinates. Okay, so that's localization, image localization. Object detection is the problem where there could be one or many objects in the image, and you have to find the bounding boxes and get the labels correct. Okay, and finally, another example of a task image which is related to images is instance segmentation, where you're really trying to find the boundary of every object object of interest in your image. And this makes sense, for example, even especially with the self-driving effort these days. For example, one example of an instance segmentation task is to segment let's say you have a frontal camera, to segment the areas as road versus non-road, as well as get the boundaries of the road correctly, or get the lane markings correctly, and so on. So those are examples of instance segmentation or image segmentation problems. Okay, so so just to kind of recap, if you have small data and you want to use neural networks, then depending on how similar the data set is, you should do feature extraction. But if it's a very different data set, then it's hard to work with small data and try to use transfer learning. If you have a lot of data, then if it's very similar data set, then you can fine tune a little bit. But if it's a different data set, but you already have a large data, then you have to fine tune a lot, which essentially means that you're kind of forgetting all the optimized parameters of the previous network. Okay. And there are many, and this is kind of very relevant for your projects. Try to use pre-trained models from, for example, PyTorch and TensorFlow already provide these, and there are many other packages, MXNet and so on. They all provide pre-trained networks as part of their package offerings. Okay, and it will be relevant for your projects. So let's. So here's an example. So I'm going to give an example of a neural network just to conclude this part on transfer learning. Because this is a network which was from 2014, so quite a few years from now. But the nice thing about this network is it has a very nice sequential layering of of different types of layers. Whereas the subsequent models that came up, for example, ResNet and so on, they have connections which jump across layers. Okay, so it's not really a really clean representation. but so you can look at this. So this network was second in the ImageNet challenge classification task, and um, from compared to AlexNet had, for example, in the first con layer had 11 cross 11 sized filters, and this network had started this idea of let's have smaller sized filters. And you can see it has a bunch of fully connected layers, a couple of cons followed by max pool, cons followed by max pool, and so on. And so I think there are about 19 layers here. And so this layered architecture really allows you to use this network as a pre-trained network for fine-tuning as well as feature extraction, because you can really just get rid of a bunch of final, like fully connected layers and reconnect to your problem and get to, let's say, 2 scores or 10 scores or whatever you want. Okay. And I think you have so VGG 19 has too many parameters, because this part, as I said, a fully connected layer and a fully connected layer 4096. If the input dimension is 4096 and there are 4096 neurons, then the number of parameters here in these two layers itself is 4096 times 4096. Okay, so the number of neurons is so number of parameters is very high. So there is a version called VGG 16, which has a little bit lesser number of parameters. Okay, because it only has 16 layers. Okay, any questions about transfer learning so far? Okay, if there are no questions, then we'll move forward. So what we have covered so far is, okay, so there is a question. So for small data sets, aren't there any instance we got to fine tune? No, you can fine tune. I mean, so here actually I should say you can also fine tune. But fine tuning, really, you're saying that you want to change the parameters, right? So which means that, as I said, the neural networks typically will have a lot of parameters. And if you only have few data points, then it doesn't make sense to change the parameters. So even if you set the learning rate to be really low, you are essentially trying to change a lot of parameters, right? Like here I was saying, there are these many parameters. So if I do fine tuning up to this point, I'm really trying to change these many parameters, which makes sense, but it's generally not preferred. But you can certainly try fine tuning with small data as well. I think the bigger question is whether your data sets are similar. For example, if you have an ImageNet-based pre-trained network and you're trying to do some classification or localization in a bunch of medical images, maybe X-rays or MRI images. Now, these domains are very different. And so you should think twice about using, because the data sets are very different, you may have to fine tune a lot to extract, to really extract good performance out of your, domain of the information from the previous data set, if at all it translates to this, let's say, data set of medical images. So I think that's more critical. Okay, fine tuning is more effort because you're actually, so you will need, so feature extraction doesn't really need any computational powers as long as you have a, for example, you don't even need a GPU, for example, because you're not touching the weights of the neural network. Once you extract the features, once you have these derived features, you can always go for a shallow model. And so that will not require heavy, let's say, tensor-based computation or GPU-based computation. But if you do want to do fine tuning, you have to load those weights into the GPU memory, and hopefully your parameters are not too many that you want to fine tune and so on. Okay. Good. So just as a mini recap, we looked at trying to understand, once you train the CNN, what are the different ways to go about trying to understand whether it did a good job discriminating across classes and so on. Then we briefly discussed how to do transfer learning, just at least what are the two modes. The simpler mode is to just feature extract from a pre-trained network and use those as or use those features and your original image as like augmented set of features if you want. Next, we'll discuss a few additional techniques which help, which have empirically seen to help the training of neural networks, okay, training of these classifiers, especially. And the first trick is, okay, let me, before getting into the first trick, um, many of these tricks, I mean, and we'll see a few today, they are, they're empirically validated. The strength of, why we're studying them, it comes from, yeah, they work really well and they have some intuition behind them. But in terms of, in terms of theoretically saying that this is the best architecture choice compared to another architecture choice, we cannot really say that from a theoretical point of view, because these are highly nonlinear functions anyway. And so comparing functions and saying one is better than the other, it's hard in terms of some sort of theory. Although there are attempts to do that these days. It's an active area of research. So with that said, these empirically validated techniques do sometimes improve the performance. For example, classification accuracy or whatever is your metric in free-form neural networks and CNNs. So we'll look at a few. First is just changing the data, or in fact, in particular, we're going to augment the data as in add more data points from our original data set. That's one technique. And the second set of techniques are all related to the model. In particular, the first one, weight initialization, it's not really a technique, but a consideration that you need to take into account, as it heavily influences how you, the parameters that you eventually get, how well they work in terms of test accuracy and so on. Okay, and two other techniques are related to the model specification itself, batch normalization and dropout. Okay. Although I'm going to talk about initialization, we will not really get into the details of the optimization techniques involved. We'll just say it's some gradient-based technique, and that's what we've been doing so far. Whenever I say learning rate, it's any gradient-based technique will generally have a learning rate. So we haven't fixed it, but there are, as you have seen in your, some of you will see in your first assignment. When you use, let's say, Keras, you get to choose the optimizer type as let's say Atom optimizer, or let's say SGD and so on. So there are variations, and we'll discuss that towards the in another lecture in this course later on. Okay, so let's start with data. Before even thinking of modeling, you want to kind of understand how is the data handled, what is its quality, is there a lot of noise, is there a lot of sampling bias, are you only collecting one class data, data related to one class a lot and another class not much, and so on. If you look at handling for image type of data, there is a lot of image data is not is actually quite resource intensive. So you really need a lot of space, and you also would prefer placing them contiguously in terms of on your hard disk, for example. Okay, so this is just for efficiency reasons for handling this type of data set. Okay, we will probably not get into the details of this. I mean, but this is something that you need to take into account if you want a high performance workflow. Second is the quality. So you want to get as clean a data as possible, but sometimes you will not be able to, maybe data collection itself is costly, then you'll have to get some cheap data. For example, if you want to, and this is something you can try after this lecture, you can actually just go to Google image search and find two classes. Okay, just search for two different types of flowers, and if you can search for the names, then you get a bunch of images. Just right click and save them, save all of them. Maybe you have 10 or 20 images for one type of flower, and 10, 20 images for the other type. Then with just these two, you can actually do the previous transfer learning with the pre-trained network like VGG 16 or ResNet. Okay, so in this case, you did not collect the data, so it's probably unclean. There may be mislabeled, like a flower might have been from some other, might have been some other type, but it just got picked up when you did that Google search. But it's fast, but unclean data. That's an example. So let's talk about augmentation. So this is the original pipeline, right? So you have a data point, xi, yi, you pass it through the network, you get a, and yi, so you pass the yi as well. And And with those two, the yi and whatever you computed here, scores, based on that, you compute a loss value. And we've discussed what are different choices of loss values before. And most prominently, we will be kind of looking at pretty much cross entropy loss or the softmax loss. Okay. So you're doing that. Now, in addition to that, we'll also do a slightly different thing, which is we'll get a different xi. So instead of xi, we'll keep everything else the same, but we'll use a different one, which is called x tilde I. Okay. Now, what is x tilde I? Of course, it's related to xi through a transformation. Okay. So so what I'm trying to say is that we have an example xi by I. We'll also create another example x tilde I by I. Okay, so that's like so if we had a transformation G which goes from xi xi to x tilde I, and if I had 10 so if I had 10 examples to begin with, if I have this transformation G, I already created 20 examples, right? 10 previously and 10 now. Okay, so so that's the idea of augmenting data. And here's an example. So G is just could be one transformation, but we can have many such transformations. So for example, if this is the original image, here is one transformation where the colors have changed. Here's another image where I've flipped along the vertical axis, and also the color has changed. Here's a crop transformation. It's a random crop. So if I apply this 10 times, I'll get different crops. And also there is a random scaling. Okay, so this is also again, if I apply it 10 times, I'll get different scales. Okay. But for all these, let's say the class is actually just UIC. Maybe we're classifying logos, whether it's a logo of UIC or not. Okay. Then for just this one original example, I got 5 additional examples. Okay, so that really augmented my data set. And this is quite widely used. And so you might have seen, I don't know how many of you have gone through PyTorch tutorial. It was linked in the last lecture's related links. So if you look at, if you have seen the PyTorch tutorial, there's this transforms dictionary with some predefined transforms that you can supply while creating your what is called a data loader. Okay, so these transforms are essentially these transformations. They augment the data so that you have more data from your original data set. Okay. So if you do these transformations and have the same class as the output, so the same yi related to them, then you can also do one more thing. At test time, also you can apply these transformations to somehow get multiple predictions and then take like a majority vote or an average of these predictions. So for example, at test time, so at test time, you already have pre-trained network. You haven't test input image. You just do all sorts of transformations. Maybe, for example, here I'm showing a bunch of boxes. So you crop the image in various sizes and then pass it through the network. Okay, of course, there's this issue of image size for the first input layer. So modulo that, if you can pass all these multiple images that are created from a single test image and pass it and get the label, then you can take an average or a majority vote. Okay? So, and in fact, for ResNet, which is the model from, I think, Microsoft, which was the winner in 2015 in the 1000 classification problem, they had images at different scales. And at each scale, they were getting lots of crops. Okay, so they were actually generating multiple predictions and then taking average. Okay, and I mean, the ones I showed above are just few examples. You can also change contrast, color. You can do rotation, stretching, and various things. Okay, and for some types of images, some transformations do not make any sense. For example, if it's an image and you're doing optical character recognition and you flip the image horizontally, so something like, so this is my name, but if you flip the image like this, then those don't reflect any more alphabets, right? So you just need to be careful of that. Yeah, and so data augmentation is not exactly it is a new relatively strong technique that you should use, but it has its root in non-image type of data sets as well, where people would add some noise to their training data to ensure that even if a slight perturbation of your feature vector was there, you would still classify it to be of certain type, for example. And there are some ideas in a signal processing field, like input dithering is what they call it, which had the same ideas. Okay. So now let's come to, so that's about the data part. So it's not really related to the model. But the next few techniques that we'll see are related to the model. So we've seen a few choices already in terms of modeling choices. One is the choice of activation function. People have converged to ReLU, although there is still many other choices like leaky ReLU and so on. And in your assignment, you have an example related to leaky ReLU. By the way, leaky ReLU just means some nonlinearity like this. So it's not exactly linear, but it's like something like that. And ReLU would be, which is 0 for the negative numbers. Okay. And we also have done a few other choices like number of layers and the number of neurons per layer, and also filter choices like the number of filters in a conv layer determines the output tensor size. Okay, and pool, whether it's max pool or average pooling and so on. There are many choices we've already done, but there are other choices that you can also use to make a difference, which are few choices one is weight initializations. This is more related to optimization of the model, and the next two are additional aspects that you can bring into your model, just like the nonlinearity. Okay, so let me talk about weight initialization first. Yeah, so weight initialization is a consideration that you need to take. It's not really a new technique, but it's a consideration for which significantly influences the performance of your trained network. Okay, because of the high nonlinearity of the loss function. So the loss function, remember, it's a function of your parameters theta, and there are, if you have 10 fully correct layers, or not 10, like if you look at the LXNet, or no, VGG 16, remember the last but two fully connected layers already had, I think the last but second fully connected layer needed to have these many parameters. This is already 10 to the power 8 bunch of numbers. Okay, it's already 100 million numbers. So, um, so, so if you really can imagine, and it's hard to imagine, but if you can imagine a space like instead of x and y axis and uh, z, and then this is x1, x2. Instead of 2 coordinates, can you imagine 10 to the power 8 coordinates? And then if you imagine a loss function, it's kind of very hard. But if you think of a loss function as a function of these 10 to the power 8 numbers or parameters, then if the loss function, it turns out that the loss function is not nice. It has lots of hills and valleys, so it's all over the place. And so gradient descent steps, gradient descent or first order type techniques, they will be heavily influenced by where you start. Okay, and so weight initialization becomes important in that sense. So, for example, if you start with weights all zeros, maybe it's a bad start, because if weights are all zeros and it somehow happens that your data set has all negative numbers and you're using ReLU nonlinearity, then you will never get a positive output on the ReLU output, and so the whole network doesn't even do anything, right? So it's very important to take into account this. There are several initialization techniques, random weight initialization, even random weight initialization. What should be the level of randomness? So is it zero mean random variables with a certain variance, or it should be uniformly random between -1 and 1 and whatnot? So there are some choices that people have figured out. So it's better to and choices of people have figured out through experimentation. So it's better to go with those choices. Okay. These weights also influence the initial activation statistics. So they remember the gradient descent step. So every time there are different, you keep changing the weight, the parameter candidates, and for each parameter candidates, you will have a certain activation profile, right? For example, some neurons don't fire, some neurons fire. So those get influenced by the where you start in terms of your weights as well. Okay. So I'm not going to comment too much on it, because there are some I think, for example, one heuristic is called Dropout Initialization. So there are different names based on the researchers who designed them, but it's better to look into the literature and figure out what's the best practices here. So the next technique, which is related to the model, is called batch normalization. It doesn't have a, I think it doesn't have a strong theoretical uh, foundation in terms of how it influences the performance of training and the eventual classifier or the network that you find. But empirically, people have found that sometimes it gives a good handle, ensures that the training is stable, okay, because there's a huge nonlinear function and gradients are passing back and forth. So gradients are passing through the huge, computational graph, so they can become unwieldy. Maybe they'll set to 0, or maybe they're exploding. So batch normalization tends to help with that. Okay, so their statistics help in this gradient propagation and therefore keep the learning stable. Okay, so what is batch normalization? So let's look at it. It's basically a very straightforward idea. It's all about, as the word says, you want to work on a batch. So a batch means a batch of examples, recall from the first lecture. So let's say we have a batch of n examples. Okay, so let's say a batch size of 64. Okay, so you take a batch, and so it turns out, and I did not probably emphasize this earlier, whenever you do backprop or whenever you use packages like Torch, PyTorch, or TensorFlow, you tend to, this batch computation happens such that every layer does not process an individual input tensor. Okay, so every layer is actually processing all the tensors related to one batch. So for example, if n is equal to 64, then let's say there is some intermediate conv layer, then that conv layer is not just acting on one input tensor related to one example. That conv layer is actually acting on all the 64 input tensors corresponding to the 64 examples that are chosen in this batch. Okay, so that's the parallelization that's actually kind of important in kind of important feature that the GPUs provide to really accelerate these computations. So normalization is all about trying to normalize activations or any intermediate computed numbers. Think of activations as just the outputs of the neurons, right? Output of a layer. So the idea is to normalize the computed numbers across the batch and then pass on the numbers to the next layer. Okay, so let's look at this example. Let's say we have n batch size is capital N. So let's say there are n rows. Okay, there are n rows. So each row corresponds to a computation, an intermediate representation of that example, right? Some intermediate vector corresponding to that, corresponding to the first example, let's say the first row. Now what you are going to do is pick a specific neuron. So each column essentially corresponds to a neuron because, as I said, each neuron works with all 64 input tensors and produces 64 numbers instead of one number, right? So if you think of each column as a neuron, then what you do is pick up across the 64 examples, pick up all the computational outputs. Okay, let's call this X. Okay, and then it just normalizes those numbers. So if normalization step is just saying that, oh, whatever these numbers are, take their mean value and divide by something like the square root of their variance. Okay. And these extra parameters, gamma and beta, you can just ignore them for now, but they can be parameters of this batch normalization operation. Okay, so think of batch normalization operation taking this x vector and producing an x hat. Okay, and so if you arrange the intermediate representations of these n examples in this batch, then the output is the same size, right? So only thing that changed is each number got rescaled and divided by something. Okay, that's the normalization step. And so this is batch normalization. This is what you do while training. So while training, at the output of a few layers, you can put batch normalization as a intermediate computation before passing on the tensor to each tensor to the next layer. Okay, so the numbers for each example get influenced by everybody else who was in that batch. Okay, so it's a little bit different from so the numbers are not independent of what computations happened with the other examples in the batch. Okay, so this is a bit different from other techniques. Now, so you can think of gamma and beta as parameters of a batch normalization. So just like a con layer will have the filter weights as parameters, just like the fully connected layer has all these, just the weight matrix as a parameter. Similarly, batch normalization layer will have parameter, let's say gamma and beta, and these can also be tuned, just like you can tune the parameters of other layers. Okay. And you can see it from the function that it's not a function which is a very messy function. It's just literally a linear function of gamma and beta. I mean, given the data is fixed, so it's a linear function, so it's easy to it's not a messy function to propagate gradients through. Okay. Now at test time, when you have a test input, then really you don't there's no batch, right? If you submit a single image to your train network and you want to get its class, then there's no batch to work with. What you do is try to remember or keep a running average of these expectation values and variance values that were used previously when you're training. Okay, if you remember, so you don't have to explicitly remember them. So it turns out that whenever you instantiate such networks, they will, these are essentially become parameters and they're retained in the model in addition to gamma and beta, so that at test time, the test input can also be rescaled appropriately, renormalized appropriately. Okay. So that's batch normalization. So if you had a previous network which looked like this, then you can add a batch normalization step to the pre-activations if you want. So which is what I've shown here, but it doesn't have to be on pre-activations, but can also be after the nonlinearity, for example. So here in this example, I'm just showing batch normalization as something which is happening after the convolution operation, but before those neurons get influenced, get transformed by the nonlinearity, which is the ReLU nonlinearity. But it doesn't have to be here. It can be anywhere. It can also be after the nonlinearity. Okay, but after the nonlinearity, if you do batch normalization, remember nonlinearity puts all the numbers to be greater than 0. So if you do batch normalization, they get recentered so that there are some numbers which are less than 0 because of this minus expectation. Okay. So that's batch normalization. So any questions about batch normalization and weight initialization? Because I'm going to go to talk about dropout soon. Okay, so let's move to dropout. Okay, so what is the idea of dropout? So dropout, you have to think of a dropout technique as a way to regularize your neural network. So we already, we did it from lecture 1 and 2. We added a regularization term, right? So gamma times, let's say, norm of the W matrix, okay? So norm of a matrix, like let's say the Frobenius norm, is just the sum of the square of the elements of the matrix. So instead of this explicit regularization, which tacks on to the objective function, and then you compute a gradient with respect to that as that this regularization term as well. Instead of that, you can think of dropout as a way to regularize your network, so as to and think of we need to think of regularization as a way to restrict our network. Okay, so that it doesn't take undesirable parameter values, as in the weight values, for example. So what we do essentially is during training, we every time we forward pass, okay, so what we do is we arbitrarily set a bunch of parameters to 0. Sorry, a bunch of neuron outputs to 0. So let's say in this very simple example, so if we're doing a forward pass, there was some input, and let's say the current weights were some numbers, and so we computed this hidden layer, hidden neuron output, right? Neurons in this hidden layer, and then all those were aggregated again to get these outputs. Okay, that's a normal operation. Now, if you do a dropout operation, what you'll do is, let's say in a particular forward pass, you'll drop a bunch of neurons. Okay, dropping the neurons is the same as saying I'm setting the some weights in my weight matrices to be 0 as well, because is equivalent, right? So if I set the output of a neuron to 0, then I can also set the, remember neuron is just a nonlinearity like sigma times x transpose some neuronal weights plus a bias, right? So either I can set the W to be 0, or I can just say this nonlinearity, this whole operation is actually equal to 0. Okay, so you set that to 0, but you still expect the remaining neurons to produce a signal, produce a score, for example, at the end of the day, and the score to be high for the appropriate class. You still expect that. Okay, so although I dropped some intermediate neurons, not just in one layer, this is just an illustrative example, you still expect the score to be high for the right class. Okay, so you want to change the parameters of the remaining guys, wherever whichever neurons are still present, so that the score for the uh, right class is high. Okay, so that's what you want to do. So that's dropout. So you can do that not just for one layer. So think of, let's say, 10-layer network. You can, let's say you implemented dropout on a couple of layers, or maybe all the layers, let's say a couple of layers. Then all you're doing is in every forward pass, you're just dropping a bunch of, computations of a bunch of neurons. And so in some sense, the network is smaller, right? Because if I drop a bunch of neurons, now there are lesser, the input signal is going through a lesser number of neurons to get to the output score, right? So in some sense, you have restricted the capacity of the network. And every time you do this dropout, you change which neurons you drop. Okay. And so because you're randomizing which neurons you're dropping, in some sense, during training, you're ensuring that irrespective of a subset of neurons dropping, the network should learn enough to still discriminate. Okay. So you're making the network use a smaller capacity, smaller capacity within itself to be able to still classify. Okay, so and so smaller than what it can actually than its nominal capacity, and that's a form of regularization. Okay. At the end of the day, and once you do this training, you have a network. That network is quite resilient. It has overrepresentation or redundancy present, right? If you once you've trained this network, so you can think of this as actually, there's one way to think of this final output or final network as some sort of an ensemble of all these dropped out networks. Okay. So another point of view, and which we already discussed, is subsampling a part of the network for each example. So we're only ensuring that even the subsample network is able to discriminate across classes, for example. Okay. So how do you actually do dropout? I mean, like, how does it work in test time, for example? So one first point is that higher probability of dropping out neurons means a stronger regularization. For example, if I drop neurons with probability 90%, which means that most neurons get dropped out in all the intermediate layers, then it's a really thin, some sort of a sparse network. So it really is, you really want to restrict the capacity of the network. Whereas if you do a very low value of dropout, like with small probability you're dropping off networks, then the network's capacity is really not that restricted. Okay. Now at test time, you can do a couple of things. At test time, you're not gonna, you can, you could do at test time. What you could do is one thing you could do is intuitively, you have a test input. You can pass the test input through the network, do the dropout, again pass the input to the network, do the dropout again and again and again. Every time you do the dropout, you get a different network, and therefore potentially slightly varying scores. You can average and take a majority vote, for example. That's one way. But another way is to perform no dropout. Okay, you don't drop out anything, so you keep all the neurons, but you ensure that all the activations are scaled appropriately by the probability of a dropout. Okay, and this is needed because if you don't drop out, then if you're not doing dropout, then the activations at any layer, right? So an example is here. An activation at any layer, it's gonna be at a different scale than when you're doing dropout. So for example, let's say we're dropping out with probability P. Okay. Which means that, let's say this was the 2-layer network from last lecture. So let's say this was the original network, W2 times max of 0, W1x plus P1 plus P2. Now with dropout, there will be an additional scaling number P. Okay, so this additional scaling number is what you will introduce at test time, while if you don't want to do dropout at test time. Okay, so this is how you compute your final scores instead of just doing W2 times max of this when you did dropout while training. Okay, so there's a way to correct for your dropout aspects if you don't do perform, if you don't do dropout at this time. So that's dropout. So let me summarize this part. So we're going to switch to, I think, NLP soon. So I'm going to summarize working with images for now, and we're going to come back to images at a later point of time. So the first, I guess, non-trivial class of neural networks that we saw in this course are convolutional neural networks, and we saw that they were very effective. At least historically, they showed a lot of promise early on in early 2010s on image-related prediction tasks. They are, I think, they are still state of the art, but now the con layers have been used along with many other architectural changes. VGG was the one which was quite sequential, but like, for example, ResNet had additional skip connections and so on. We have not discussed that, but overall, the con layer and its use in the overall network architecture has really impacted image-based prediction tasks. Now, as I said earlier, they really exploit locality of like detecting local features as well as spatial inference where the feature is. For example, an edge, whether it's where it's in the image, they take that in account. The con layer really exploits these aspects of images. There were a lot of design choices that need to be made in addition to the the zero thought of ones, like how many hidden layers and how many neurons and so on. Like use of batch norm, use of dropout, which place should I drop out, as in which network I should which layer I need to employ dropout at. But they have been empirically validated, some of these choices, and it's better to go with those choices in your specific data set. And so for your specific data set, it may turn out that the empirically well-known choice may be suboptimal, and instead you should do something else. So it could still be the case because all these are general trends which are not hold for your specific data set. And so today we also saw how to understand whether your CNN is actually working after it's been trained, like doing projections onto 2 dimensions, or doing occlusion based quick analysis, post hoc analysis really helps. And transfer learning is the way to go, especially if you don't have large data. It's always good to fine tune a pre-existing network and work with that. And finally we saw a few things like data augmentation, which really makes sense for images. And this is quite standard. You will see any PyTorch, and in our own CNN example notebook, we do data augmentation. On the model side, we have batch normalization and dropout. But on the optimization side, weight initialization was important. But there are many other aspects of optimization that we did not discuss. Later on, we'll try to revisit this topic. Okay. So any questions at this point? Can we do batch normalization on input? So input is really not a computational layer, right? Input is just some sort of a redundant layer. That's why even if there's an input, we kind of ignore the input and say that, like the picture I had, we call this a 2-layer network because input is really redundant, right? It's not really the output of any computation. So, but batch normalization at this layer just means, so if you have a batch of, let's say, 64 images, you're saying whether I should average, like take let's say the first top left corner pixel for each of the image, let's say in the first channel, let's say red channel, and then do this normalization. I don't have an answer to that question. You should try to experiment with that. Yeah. I mean, a priori, it doesn't seem, I cannot rule it out, but yeah. So any other questions?
And for dropout, so we do, like, let's say if we are dropping 50% of neuron for the first pass,
yeah,
and when we do back propagation, we keep the same neurons dropped and do like full.
Yeah. So for a single pass, so let's say you're looking at one batch, or let's say you're looking at one batch. For that batch's forward pass, you dropped a bunch of neurons. then for that whole computation of updating of weights as well, you ignore those neurons. It's as if you're working with a restricted smaller network.
Okay.
Okay. So that's why you can interpret this whole dropout based training as, at the end of the day, getting you an ensemble of neural networks, because for each batch you essentially train with a slightly different subnetwork, and then you're basically saying at test time I'm not dropping anything, so this is like an overlapping set of different subnetworks of the or full architecture. Okay, that's
Okay.
why it's like an ensemble point of view.
Okay, cool. Thank you.
Yeah. So, but anyway, to just summarize for your question, for a single pass, you don't you once you drop the neurons, you forget it. So you have a subnetwork, only backward pass through that subnetwork or the sub computational graph, and update the weights that are still remaining.
Okay. Yep. Thank you.
Any other questions? So if not, I just wanted to quickly do one thing, which is really ask people to start start playing around with TensorFlow. Sorry, not TensorFlow, but Google Colab. It's a great resource, especially because you may need GPU computation for, let's say, CIFAR 10 image classification. It's a 10 class classification problem, but still, for those types of problems, your CPU, you will see that it'll take a lot more time than using a GPU. And there are some decent for entry level, to learn deep learning, there are some decent GPUs which are available for free on Google Colab. So, and it's very accessible, and there's nice features, which some additional features that are there which you cannot get from just using Jupyter notebooks. So Jupyter notebooks are really great, especially if you have a server with you, like on Amazon. Let's say if you get an EC2 server with a GPU, then just use a Jupyter notebook there. And if you have proprietary data. But with Colab, you can also do collaboration. So you can actually share that notebook with your teaching staff or your other your colleagues and your classmates if you want. So here, I think I'm trying to show just importing our own Git page, and if you see in that repository, it's a public repository. So we have all the things that we saw from last week. Okay, so let's open this one. So you can open any notebook as long as it's on GitHub public repo. So you can just really run through it without wondering whether it's being saved somewhere or not. Of course, you can always save, if you modify that notebook, you can save it on your own Google Drive. And so, but you may need some modifications. For example, for this CNN example that I have, there is a need to download some data, which I did when I was doing Jupyter on my local machine. But I don't know if I can download it here, so I'll not run it here. But you can see, so I just want to quickly walk through this notebook. And I also want to say one more thing, which is this link. Okay, so this is, I remember I told you visualization of low dimensional embedding. There's this technique called UMAP. Okay, just like TSNE or even PCA, which is used for dimensional reduction. You can also use UMAP as a way to do nonlinear dimensional reduction. So here on their GitHub repo page, they show an example of doing that with MNIST. I think the 784 dimensional MNIST dataset. Remember, it was 28 cross 28 size grayscale images, so it's 784 dimensional if you think of them as vectors. You can actually drop them into 2 dimensions and see that the classes really separate. Okay, so let me come back to this notebook. First thing I want you to start working with, if you've not yet, is start playing with the PyTorch tutorial notebooks. Okay, so for example, this notebook is actually from PyTorch. From the PyTorch tutorial page, and it's importing a bunch of torch related objects and classes. So I think the important thing related to our lecture today was this. Okay, so data transformations. So you can see there's a bunch of transformations that have been chosen for training and validation. So resize the image. That's okay. That's to ensure that the images are all same size. You know, you do some cropping, but for example, on training side, you can see there's a bunch of transformations, random resize crop, and then random horizontal flip. Okay, so why did they do these transformations? Because I think, so they're trying to do fine tuning. So to do fine tuning, they're trying to use the ImageNet pre-trained network. In this case, I think they're using ResNet 18, I think. Um, so for ResNet 18, the input image size has to be a certain size, which is 224 cross 224. Okay, so 224 pixels wide and that height. So you can actually do a crop so that you get to that size. And there's additional numbers. So these numbers are actually data pre-processing parameters, which are like the median um, numbers needed that were used, that are some sort of like a derived summary statistic of ImageNet dataset. Okay, so you just have to use these numbers to normalize your images. Okay, and then so what does this do? This operation essentially says do these operations and produce a tensor. So although you had an original image, the let's say 300 cross 300 cross 3 pixel image of, in this case, we are classifying ants versus bees, which are just generally connected from the internet. So we have some size image. They're doing a bunch of transformations, and sometimes for training, they're also doing transformations that are essentially data augmentation transformations. At the end of the day, you are getting an intermediate tensor. Okay, the tensor goes through all these operations and produce the tensor you get is a 224 cross 224 cross 3 size tensor. Okay, and and uh, and the transformations are applied here, right? So when you're creating the dataset object itself, so this dataset object, so this datasets object is from where is this? Yeah. So from torch vision, we're getting the datasets object and the transforms object that is which has the or the class which has these functions. Okay. So the datasets will create an intermediate dataset object, which is essentially not a full, which it doesn't read all your images into memory. Okay. This is just some sort of a map which says, oh, for the first data point, this is the location of the image and this is the label and so on. Okay. And data loaders are another essentially these are data loaders are the objects that you use to generate your batches in your training loop. Okay, so these are two important classes, data sets and data loaders, that you should look up. Okay, how it's working with this data, which is the example that we have on the lecture page as well. And you can see the images by just using plot.imshow just to see what are the bees and the what are the classes. Like these are bees and the first one is ants. And then training loop is okay. We're getting the training loop already. Okay. Um, Okay, yeah. So we just define the training of the model. So because this is not specific to this is not specific to any CNN model. Okay, for any model you have to use the same type of training loop. So that's written here. So that I think we'll skip for now. And same with visualizing the model. So now what's the model? The model this is the pre-trained models. Okay, all you need to do is from Tosh Vision import models and models.resnet and pre-trained is equal to true. Gives you that model architecture. Okay, and then you can find the input features and you can replace the final. You can place the final layer to be a two-class classifier. So the final scores are essentially changed to 2 here. Okay, so the fully connected layer, the last layer is the fully connected layer. That layer's input features are being copied here. So a number of input features, and they are being changed to the last layer is being changed to this. Okay, so that number of input features, and the output has to be 2 instead of 1,000. So that's the fine tuning idea here. Sorry, yeah, that's the transfer learning idea here. And anything else? Learning rates. We will talk about optimization in a lecture later. later on. And yeah, and I would try to suggest to run this notebook on Colab rather than your own machine. Unless you have a GPU, then it's great. And so on this example notebook, you have both types of fine tuning. So I highly recommend trying it out after this class. Okay, so if there are any questions, you can ask. Otherwise, thank you so much. I think we went 30 seconds over time. Do I have office hours? So we can schedule office hours by appointment or via Slack. Yeah. So students have already done that. So you can reach out to me and we can have one-on-one sessions, Zoom sessions. So let me pause the record, stop the recording.